So let's look at an actual example. So let's say that we have a simple function that sums up or adds up a list of numeric objects. So let's say we got this function called addNums, to which you pass a vector. It's a vector of numbers. So down here is an example of how you might call that function. So look right here, you got vector. Okay, with the C function, you pass it to addNums, so that vector comes right in here. And all you're going to do inside that function is you want to add up all the numbers. So you calculate the length of the vector. You initialize some kind of an aggregating variable, and then you go from 1 to L. That's the length L right here. Basically loop from 1 up to L. And all you simply do is you add up each element in the vector. V sub I is each element in the vector, 1 by 1. Add it to S, and we return S. So S is going to simply get printed out right here. In this case, I think it would be 29 or whatever it is. So it's a pretty straightforward little function. So to evaluate the running time of this algorithm, this program, this function, we need to basically ask, well, how many steps does it take? So in this case, we can count the number of times it performs the addition. S gets assigned S plus V sub I. So for a vector with n elements, it would take about n steps. Well, no, sorry, it would take exactly n steps because the loop loops from 1 through n, which is the number of elements in the list. So therefore, that means that this function has a time complexity of O of n because it increases linearly with the size of the input. So that's its asymptotic or its behavioral assessment of the algorithm. Now, of course, we can also measure the actual performance. I could, for example, obviously I'm going to have to do this with a much larger vector to make sure it's actually significant. Let's say I want to add up numbers from 1 through a million. I can do that by calling system.time. And then I'll compare that against adding up a vector of 1 to 2 million, exactly twice as large, and exactly what you would expect happens right here. You have initially 0.64 seconds versus 1.23 seconds, about twice as large. It's obviously not exactly twice as large. There's some, few milliseconds here or there depending on how memory is being allocated and so on. That's not really important, but what's really important is the fact that we have about twice as long. And if you were to run this from 1 through 4 million, it would take about most likely somewhere around 2.4, 2.5 seconds to run. So it's important that we understand how to count basic steps. So here's a poor implementation. So novice programmers often write this code to add a vector of numbers. Instead of assigning the length of the vector to a variable, they would actually just simply put the length of the vector right in here and run the code. Code runs just fine. The question now becomes, what is the behavior of that program? Well, that actually depends on how many steps is involved in calculating the length of a vector. Now, I happen to know that in R it's actually O of 1, so it's not really a big deal, but because of the way vectors are implemented. But if there was a different data structure like a list that might be implemented through a linked list, it would actually be O of n, because you would have to actually traverse the entire list to count how many elements it has. So then that means this is O of n that takes n steps to calculate. And how often do you calculate it? Well, once for every element in it, so you keep going through it over and over and over again. So if this loop right here runs n times based on the size of the input, and length takes O of n steps, that means the entire algorithm here would be O of n squared, because you would have to do that step n times. So suddenly, instead of having a behavior of O of n, you would have now a behavior of O of n squared. And all you really did was you innocently put the length calculation of your data structure as part of the loop. You tried it out for a small number of inputs, worked just fine. So you figured since it gave you the right result, you have a properly functioning program. Well, it's properly functioning, but its space complexity and its time complexity is very different from the previous implementation. Now, of course, that means I would have to also know how long length takes to run. Now, length is not something I wrote. It's actually something that comes from the library. So since I really don't know what the runtime behavior of length is, I would have to look it up. And for every library function used, particularly those that work with vectors or other large data structures, data frames, lists, matrices, and so on, you need to understand their time complexity. Otherwise, you might use them in a way that would result in very, very poorly performing algorithms when you apply them to much larger data sets. Now here are the time complexities of some basic operations that you might need to carry out. So for example, to access the ith element in a list, vector of some kind, is typically O of 1 if it's implemented using an array. If it's implemented using a linked list, it would be O sub n. To search a list sequentially would be O sub n. We just talked about this earlier. You would have to, on average, search half the number of elements, or in the worst case, all the elements, which means it is linearly related to the number of inputs that you, or the size of the input. To find an element in a sorted list is O of log n, because we typically can do a binary search, which has a behavior that is logarithmically related to the number of elements in that sorted list. Very important that it's sorted. If it's unsorted, then it's O of n. Sorting, well, it takes a different amount of time depending on what kind of a sorting algorithm you use. Quicksort takes n of n log n. Insertion sort is n squared on average, but much better, by the way, in the best case behavior. So if it's a partially sorted array, it's actually quite a bit better. It actually approximates O of n. Selection sort is O of n squared in the best case. So selection sort is often a very good sorting algorithm. So if you use a sorting algorithm in, or sorting procedure in R to retrieve data in a sorted fashion, or to output in a sorted fashion, you better know what the runtime behavior is of the sorting algorithm that you're going to use. And you understand how that behavior changes as the size of the input changes. Of course, aside from time complexity, we also have to assess space complexity. After all, programs use memory and storage, so that the computer scientist requires an assessment of a program's use of that critical resource, again using the big O notation. For example, loading data into a vector has a space complexity of O of n, since you would need twice as much memory for a vector that is twice as big. So this, of course, is very important for any type of internal memory data storage, or even for storing data externally in a database, because you need to calculate disk space. And of course, if data gets transmitted over a network from a client to a server, that of course would dramatically increase the amount of time it takes to transmit the data. So to summarize, in this lesson you learned that the time and space complexity of a program must be calculated to understand its behavior as input size increases. Complexity of time and space is given using big O notation, and that the runtime of a function can be measured directly in R using system.time.